Good morning everyone. Today we're going to learn about the divide and conquer technique. We're going to discuss some divide and conquer based algorithms, how to do the time complexity of those algorithms, master theorems, and how to use the master theorem in analyzing the divide and conquer algorithms. Divide and conquer is one of the powerful techniques for the algorithm designing. It leads to naturally recursive algorithms, and you can discuss the time complexity of those algorithms based on a divide and conquer recurrence relation. The main idea of a divide and conquer algorithm can be followed by these three steps. In the first step, we divide the problem instance into a set of smaller subproblems of the same form. Then in the conquer step, we conquer the subproblems by solving them recursively. And once we have the solution of our subproblems, then the next step, we're going to combine the solutions to obtain the solution of the original problem. There are many searching and sorting algorithms you can put in this category. In this lecture, we're going to focus on one searching algorithm, which is our binary search algorithm, and one sorting algorithm, which is going to be the merge sort algorithm. In the binary search algorithm, the input is a sorted array A of n elements and a key element x. The goal here is to check if that key element x is present in the array A or not, and if so, then return the index of the element, otherwise return an error message. To understand how the idea of a binary search algorithm works, let's take an array A of size 7, where the elements are 2, 4, 6, 9, 10, 14 and 17, which is already an array in increasing order. Then we are trying to search a key where x is going to be equal to 10, where the number of elements in my array n is going to be equal to 7. Then the goal here is to check whether x is equal to 10 is present in that array or not. In binary search algorithm, we follow the divide and conquer approach. So in the first step, for my sorted array of size 7, I'm going to compute my mid index, where mid can be obtained by following this formula. Is going to be the floor value of I plus j divided by 2. My I index and j index is the first index and last index of my given array, and the first index I is going to be equal to 1, and the last index is going to be j is equal to 7. So my mid index is going to be 1 plus 7 divided by 2 and take the floor value, which is going to be equal to 4. Now if you look at the A of 4 in this given array, that's going to be equal to 9. And I'm trying to search the element x is equal to 10, whether that is present in that array or not. And my A of mid, which is 4 here, is not going to be equal to 10. So in my divide step, I'm going to divide this given array of 7 elements into two different subarray. The left subarray is going to have 4 elements starting from I is equal to 1 index to the mid index, which is 4 here. And the next array is going to have an index from I is equal to mid plus 1 to I is equal to 7, which is the end index here. Okay. Then in my conquer step, I'm going to compare the A of 4 value, which is 9, and 9 is less than 10, which is my x value. So I'm going to discard this left array, and in my conquer step, I'm only going to consider the right array because there's a possibility that my x will be in the right array. Then in my conquer step, I'm going to do the solution of this conquer problem recursively. So again, I'm going to compute my mid index with respect to this right subarray. My starting index is 1 here, I equal to 1. My end index is going to be 3 here, and my mid index is going to be the floor value of 1 plus 3 divided by 2, which is 2 here. So the mid element of this subarray now is going to be, let's suppose if this is my B of 2 is going to be equal to 14, and 14 is not going to be equal to x. So then again I'm going to follow my divide step. So in my divide step, I'm going to break this array with 3 element into an array of 2 element and array with 1 element, where my left array will have an index from I equal to 1 to I equal to mid, and my right array will only have a single element, which is I equal to mid plus 1. Again, I'm going to check the condition whether b of mid, which is basically equal to b of 2, and b of 2 in that case is 14, and 14 is greater than my x, which was 10 here. So this time I'm going to discard this. I'm going to discard this right array, and then I'm going to work in a recursive way in my conquer step on the left array, which is having only 2 elements, 10 and 14. Again, I'm going to do the computation of the mid index for this array with 2 elements. The first element is 10, another element is 14. So my mid index is going to be the floor value of 1 plus 2 divided by 2, and the mid value is going to be equal to 1. So in this case, let's suppose my C of mid, if this is my C array, then it's going to be equal to 10, and 10 is going to be equal to my x. So I found my element x, which is the key element here inside my array. So that's the way this binary search algorithm is going to work. So the main idea is you're going to look at the given array, which should be in the sorted fashion. Then you're going to look at the mid element, and you're going to compare the mid element with the element which you have to search. If they are equal, then you found your element. Then if they are less than your mid element is less than your key element, you're going to discard the left array. If the mid element is going to be larger than your key element, you're going to discard the right array. Okay, and you're always going to work on either on the left array or on the right array, and you do it in a recursive way. The pseudocode of the binary search algorithm is given in the form of the following recursive algorithm, formed based on the divide, conquer and combine steps. So it's following the divide and conquer algorithm. My recursive binary search is going to be the name of my algorithm. A is going to be an array, sorted array. X is going to be the element which I'm going to search in this sorted array. I and j are the starting and the end index of my array. So in my first step of this divide and conquer algorithm, in the divide step, I'm going to check the middle element, and first I'm going to compute this mid index by following the formula. Is going to be the floor value of I plus j divided by 2, and then I'm going to check whether a of this mid index is going to be equal to x, the element which I'm trying to search in this array, and if it is present, then I'm going to return this index mid. So in this step, I'm going to decide whether I'm going to break my original problem into subproblems or not, and it can be decided based on whether a of mid is greater than x or whether a of mid is less than x. So up to here, this is your divide part of the algorithm. So then you're going to check if this case does not follow that a of mid is going to be equal to x, then two more cases may happen that a of mid is going to be greater than x. If a of mid is greater than x, then you're going to return this recursive binary search algorithm, which is going to be a recursive way to call this algorithm on an array A to search an element x, where the starting index is I and the end index is mid. So in this case, when a of mid is greater than x, I'm going to discard my right part of the array, which is starting from an index of mid plus 1 up to the end index. Otherwise, if this condition does not satisfy, then I'm going to call my recursive binary search algorithm, where I'm going to discard the left array and I'm going to consider the right array to do the further search. And A is going to be my array, X is going to be the element which I'm trying to search. I'm going to consider my starting index start from mid plus 1 and all the way up to the end index, which is the J index. So this part of the algorithm, when you recursively call your original algorithm to solve the subproblems, this is basically your conquer step. And remember, in the conquer step, you're going to throw away half of the array, either the right array here or the left array here. You're going to throw it away, depends on whether you satisfy this condition or not. And then you're going to search this element X in the remaining half of the array. Okay, and you keep on following this divide and conquer steps of this algorithm, while the combine step in this algorithm is nothing, because this is a searching algorithm which you can easily solve based on this divide and conquer step in a recursive fashion. So this binary search algorithm is one kind of a divide and conquer algorithm, where in the divide step you're going to check the middle element, and then on the basis of that we're going to create two subproblems from my original problem. But in my conquer step, depends on whether A of mid is greater than X or otherwise, we're going to discard one of the part of the array. Either it's going to be the right part of the array or the left part of the array. So we can say in a binary search algorithm, we always throw away half of the array and search the key element in other half of the array. So a divide and conquer algorithm which throw away a fraction of the input and recursively works on the other part of the input, those kind of a special divide and conquer algorithm, you call them as a prone and search algorithm. And your binary search algorithm is one example of those prone and search algorithm. When it comes to the time complexity of this algorithm, then we can say depends on my size of an input array. I can say if my input array have a single element, then just on the basis of only one comparison, I can decide whether my key element is present in my array or not. So if T of n represent the time complexity of my binary search algorithm for an input of size n, and if my array will have only a single element, then on the basis of one comparison, I can decide whether the key element is present there or not. So by using that factor, I can say my T of 1 is going to be equal to 1. Okay, because my input size here is input size of my array is 1. Okay, and my number of comparison is going to be 1. When it comes to in general for any size n greater than equal to 2, then I can follow this recursive approach, and based on my recursive approach, if I count my number of comparison, so I can say the total number of comparison to search an element X in a given array of size n, which you can say is T of n, is the complexity of doing that, is going to be equal to, recursively you can say in every conquer step, you're going to divide the original problem of size n into two subproblems of size n by 2. So, but one of the array you are discarding it, so you are only searching the key element either in the left array or in the right array. So this is going to be equal to T of n by 2, which is the time complexity of searching an element in either in the left subarray or in the right subarray, and the size of this left and right subarray will be of n by 2, and plus extra comparison you are doing. The one comparison you are doing just to check whether the mid element is going to be your searching element or not. And you are doing one more comparison to decide which of the array you want to discard. Okay, so this first comparison you are doing just to check X, and this second comparison you are doing to discard your left or right part of the array. So you can say overall the time complexity of binary search algorithm T of n function, you can say, is going to be equal to T of n by 2 and plus of 2. And then you can try to prove that this T of n is big theta of log of n, or you can also try to prove that T of n is big O of log of n. Now to prove that T of n is big theta of log of n, where I have the recurrence relation, which is T of 1 is going to be equal to 1 and T of n is going to be equal to T of n half plus 2 for any value of n greater than or equal to 2. Now to write the proof of this result, we can assume that there are even number of elements in your given sorted array A, and those element n can be written in the form of 2 to the power k for some integer k. Okay, so this is the assumption which I'm starting with, so that my sorted array will be of n element, where the n is going to be some even number which can be represented in the form of 2 to the power k. And since n can be written as 2 to the power k, this will convert my recurrence relation T of n is going to be equal to T of n half plus 2. And if I replace n is equal to 2 to the power k, n by 2 is going to be 2 to the power k minus 1. So this side will be T of 2 to the power k. This side will be T of 2 to the power k minus 1. And plus of 2 is going to remain as it is. Now if I define that my A of k represent T of 2 to the power k, then we can write this above recurrence relation, this one, into the form that this side will be your A of k and this side will be your A of k minus 1 plus of 2, where my initial condition T of 1 is going to be equal to 1 will be converted to as T of 2 to the power 0 equal to 1. And if I use this definition of A of k is going to be equal to T to the power k here, so I can write this initial condition is A of 0 is going to be equal to 1. N is going to be 2 to the power k. So the above recurrence relation which was given in terms of T of n can be converted into the following form, where my initial condition is A of 0 is going to be equal to 1, and then A of k can be written as A of k minus 2 plus of 2. Okay. Now to solve this recurrence relation, we can follow the substitution method, where I'm going to look at the kth term of my sequence, which is going to be the solution of this recurrence relation. So A of k can be written as A of k minus 1 plus of 2. And if I replace this A of k minus 1 here by following this recurrence relation, that A of k minus 1 can be written as A of k minus 2 plus of 2. So this side will become A of k minus 2 plus of 2, and plus of 2 is going to remain as it is. If you replace A of k minus 2 by A of k minus 3 plus of 2, this plus of 2 remain as it is, this plus of 2 is going to remain as it is. So you can rearrange those terms and you can write that this side will be your A of k minus 3, and then you have a plus of 2 here, plus of 2 here, and plus of 2 here, which can be written as A of k minus 3 plus 3 times of 2, because you are adding 2 3 times, so you can represent as 3 times of 2. So you will have a relation between your A of k term and with your A of k minus 3 term. So whenever A of k is related with A of k minus 3, so you're going to multiply this 2 by this 3. So if you keep on following the same thing and do the substitution for your k minus 3 in term of k minus 4, k minus 4 in term of k minus 5, so after certain number of steps, you can relate this A of k with A of k minus k, and then plus k times of this 2. okay, which can be written as a of 0, because a of k minus k is your a of 0, plus 2 times of k. Now if you use the initial condition that a of 0 is 1, so you can write this a of k terms as 1 plus 2 of k, okay. That's going to be the general solution of this recurrence relation in term of k. But now since you followed this change of variable, you want to write the solution in term of n. So we start with the assumption that n was equal to 2 to the power k. So we can take the log of both sides. This side will be your log of n. This side will be your log of 2 to the power k. If you simplify, this side is going to remain same as log of n. This side will simplify to k times log of 2. So k can be written as log of n divided by log of 2, which you can write as log of n with the base 2. So after simplification, you can say the k can be written as log of n base of 2, which if you put in your a of k solution, then a of k was 2k plus 1. You put the value of k as log n base 2. So this side will become 2 times of log n base 2 plus of 1. Now if you replace your a of k terms with your t to the power k term, and since 2 to the power k was your n, so this can be written as t of n. So this side a of k will become t of n, and this side is going to remain as it is, okay. So you can write your t of n is going to be equal to 2 times log of n with base 2 plus of 1. And for this function t of n function, you can easily prove that's going to be, either you can say it's going to be a big O of log of n with the base 2, or you can prove it's going to be a big theta of log of n with the base 2. So by following that approach, we can say the time complexity of the binary search algorithm t of n is a big theta of log of n with the base 2. So we have seen one example of a divide and conquer algorithm in terms of your searching algorithm, and we discussed the binary search algorithm and the time complexity of the binary search algorithm. Now let's take another example of your divide and conquer algorithm, and this time we're going to look at the sorting algorithm, and we're going to consider this merge sort algorithm where the input is going to be an array with n number of elements. And let's suppose P and R is my starting and end index of this array. And the goal here is to sort an element in this array in a non-decreasing order. The merge sort algorithm can be explained with the help of following divide and conquer steps. So if the given array will have only a single element, that means if my n is going to be equal to 1, then I will do nothing. Because if I have only single element in my array, is already in a sorted fashion. Then in the divide step, if my array A will be of size n, I'm going to divide them into 2 parts, and then I'm going to recursively sort each part by following this conquer step, where I'm going to recursively going to call this algorithm. And once I have 2 sorted arrays, I can merge them together in this combine step to get the solution of my original problem. So if I follow this divide, conquer and combine step, then I can represent my merge sort algorithm as a recursive algorithm by following this divide and conquer technique. An example to see how this merge sort algorithm will work. So my input is going to be an unsorted array, and let's suppose I have an array A which have 4 elements, and right now they are not following certain ordering, so stand 2, 5 and 3. So I want to have an output in the form of a sorted array where the elements are going to be in a increasing order, so like 2, 3, 5 and 10. So the way my merge sort algorithm will work here, I'm going to follow this divide, conquer and then the combine step. So in my divide, I'm going to look at the original given array, which will be of size n, and I'm going to divide them into 2 parts. So my original problem of size 4, I can divide into 2 subproblems of size 2 in this step. And then further, I can try to sort this part of the array, the left part of the array, and the right part of this array by following this conquer step, where I'm going to recursively sort both part of the array. Then again I'm going to recall this in a recursive way. So I'm going to divide them into equal parts. So this side will have only part 10, this side will have only 2, this side of this right part of the algorithm will have 5, this side will have a 3. And then once I have all those left and right part in a sorted fashion, I can combine them in following my combine step. So this 10 and 2 I can combine and I can put them in order. This side will becomes 2 and 10, and which is a merge algorithm I'm going to use. This 5 and 3 I can put them in a sorting order and I can merge them together. This will becomes 3 and 5. And then again following my combine step, I can merge these two array, 2 and 10 and 3 and 5, and I can put them in a form of by merging step in the form of 2, 3, 5 and 10, which is going to be a sorted array and which is going to be my output. So if I follow my divide step and if I follow my conquer step, where I'm going to divide the original problem into the subproblems, and then in the conquer I'm going to solve these subproblems recursively, and once they have in a sorted fashion, I'm going to combine all those solution of the subproblems to get the solution of my original problem. So the pseudocode of this merge sort algorithm can be represented as merge sort is going to be my algorithm. I'm going to pass an array A with starting index P and index R. So if my start index P is less than R, I'm going to find this kind of a middle index, which is the floor value of R minus P divided by 2. And based on this middle index Q, I'm going to divide my original problem into two subproblems, and I will call this algorithm recursively in my conquer steps to solve those subproblems. The first subproblems is going to be the given array A, but the start index is going to remain same P, and I'm going to consider up to the index Q. So that's the left part of my given array. And then I'm going to look at the right part of my given array, which is start from index Q plus 1 and all the way up to R. Now on this conquer step, I'm going to recursively call this merge sort algorithm such that I can sort the left and right array. And once I have the solution of my subproblems, I can call this combine steps, where I'm going to look at the solution of my subproblems and I'm going to merge them together. Okay, and that's where I can have the solution in a sorted array form. If this condition of P is not less than R, then I can have a message the array is going to be either empty or have only a single element. When it comes to the time complexity of this problem, so if let's suppose T of n is the time complexity of the total merge sort algorithm for an array of size n, and if you just count the total number of comparison which you have to perform in this merge sort algorithm, then you can say, based on this divide and conquer approach, you are dividing the original problem of size n into two subproblems of size n by 2. So the total number of comparison here can be written as 2 times of the total number of comparison which is present in solving those subproblems of size n by 2, and plus this n, and this n number of comparison is coming from this combine step. The total number of comparison in this combine step is going to be equal to n, because in this combine step you are going to merge two subarrays of size n by 2 which already are in a sorted order. But once you're going to put them into a larger array of size n, then the maximum number of comparison which you have to perform is going to be equal to n. And that's basically with respect to your worst case scenario. Now you want to prove that this time complexity of the merge sort algorithm, which you can put them in the form of the following recurrence relation, that T of n is going to be equal to 2 times of Tn by 2 plus of n, where the initial condition is t of 1 is going to be equal to 1. Then you can conclude that t of n is big theta of n log n. And you can also conclude that t of n is big O of n log n. Since big theta of n log n also include the definition of big O, so you're going to write the proof for big theta, and the proof also holds for your big O notation. So again, we're going to put an assumption. Since this is a sorting algorithm, so we can assume that there are some even number of elements in your array, and those number can be written as in the form of 2 to the power k for some integer k. Then you can put this n is equal to 2 to the power k as your change of variable into your recurrence relation. Then your recurrence relation t of n is going to be equal to 2 times of tn by 2 plus of n will convert into the following form. This side will be t 2 to the power k. This side will be 2 times t 2 to the power k minus 1, and the n will be equal to 2 to the power k. Okay. Now if you want to represent your t 2 to the power k as your new kind of a kth element of your sequence as a of k, so you can say if you define a of k as t 2 to the power k, then you can transform the above recurrence relation as this side t 2 to the power k. So from your above recurrence relation, this side will become a of k, and this side will become 2 times a of k minus 1 plus 2 of k. While your initial condition, which was t of 1 is going to be equal to 1, you can write as t of 1 is nothing but t of 2 to the power 0 is going to be equal to 1. And if you follow this notation of a of k as t 2 to the power k, then t of 1 can be written as t of 2 to the power 0, which you can represent as a of 0. So t of 2 to the power 0 equal to 1 can be written as a of 0 is going to be equal to 1. Now you want to solve this recurrence relation, and in solving this recurrence relation we can follow our substitution method. So this side you can write a of k in terms of 2 times of a k minus 1 plus 2 of k, where you can replace this a of k minus 1 terms as 2 times of a k minus 2 plus 2 to the power k minus 1. And if you simplify, that this can be written as 2 times of 2, which is 2 square times of a k minus 2, and plus 2 multiply with 2 of k minus 1 is going to be your 2 of k, and then your 2 of k is going to be equal to your 2 of k. So which you can write as 2 to the power 2 times a of k minus 2 plus you are adding 2 to the power k, 2 times is 2 times 2 to the power k. Okay. So you are saying that a of k terms after following this one step of the substitution can be written as 2 square a of k minus 2 plus 2 times 2 to the power k. Now on substituting a of k minus 2 in terms of a k minus 3 and a k minus 3 in terms of a k minus 4 and all the way up to a k minus k, you can say a of k is related with your a of k minus k, as a of k can be written as 2 to the power k times a of k minus k plus k times of 2 to the power k, where a of k minus k is nothing but a of 0. This side 2 of k is going to remain same, and this side k times 2 to the power k is going to remain same. Now if you use your initial condition that a of 0 is 1, so you can say this side is 2 to the power k, this is k times 2 to the power k, so you can represent your a of k is k plus 1 times 2 to the power k. So this is the solution of your recurrence relation in terms of 2 to the power k. Now since we have assumed in your change of variable n was equal to 2 to the power k, so by taking the log of both sides, we can say k is going to be equal to log of n with the base 2. And this solution a of k can be written in terms of your t of n, where k can be replaced in terms of n. So k is going to be your log of n with the base 2 plus 1 is going to remain same, and 2 to the power k from this substitution you can write as going to be equal to n. So for this function, which is written as the product of n times log of n, you can easily prove based on your big theta definition that T of n is a big theta of n log n. So in case of my merge sort algorithm, I proved here that the time complexity of the merge sort algorithm is big theta of n log n, and you can also make a statement that T of n is big O of n log of n with the base 2. Okay. So in this lecture we have seen two examples, one example of a binary search algorithm, one example of a merge sort algorithm, and in both cases we wrote the time complexity of the function in terms of your divide and conquer recurrence relation. So in general you can say the divide and conquer recurrence relation will be of the following form, when you can write as T of n, the time complexity for any problem of size n, can be written as a times of T of n divided by b plus f of n, where by following your divide and conquer algorithm you are saying that your original problem of size n you are dividing into a number of subproblems, okay, of size n by b, and f of n is the some extra operations which you will be needed when you follow your combined steps. Okay, so n is the original size of the problem, a is your the total number of subproblems you are dividing in your divide steps, n by b is your size of your subproblems, and now f of n is the extra operations you will be needed in your combined steps when you write the solution of your original problem by combining the solution of your subproblems. So any relation of this form you will say is a divide and conquer recurrence relation. Now to get the big O or big theta estimate of such kind of a divide and conquer recurrence relation, you can have this result which is based on your master theorem. So the master theorem for your divide and conquer recurrence relation, which can be written in the form of T of n is going to be equal to a times T of n by b plus f of n, where a and c are greater than or equal to 1, d is going to be non-negative integer, and b is going to be greater than 1. If we assume that the size of the original problem n can be written as b to the power k form for some integers b and k, and if f of n is written as c times n to the power d form, or you can say f of n is big theta of n to the power d, then you will have these three results. And the first result is, if your a is less than b to the power d, then you can conclude that T of n is big theta of n to the power d. The another case, when a is going to be equal to b to the power d, in that case your T of n is big theta of n to the power d times log of n. In your third case, if your a is greater than b to the power d, then you can conclude that T of n is big theta of n to the power log a with base b. So master theorem is a way where you can conclude the time complexity of your divide and conquer algorithm, where the time complexity is written in the form of the following divide and conquer recurrence relation. And if you assume that n can be written as b to the power k, where n is the original size of your problem, and you are dividing the original problem into a number of subproblems, where every subproblems will be of size n divided by b, and f of n is the extra number of operations you will be needed in doing the combined steps. And if the extra operations in the combined steps can be written as c n to the power d form, which is you are assuming that if f of n is big theta of n to the power d, then you will have these three cases in your master theorem. So depends on the relationship between a and b to the power d. You will either say t of n is big theta of n to the power d if a is less than b to the power d, or either you will conclude that t of n is big theta of n to the power d log of n if a is going to be equal to b to the power d. Otherwise you will say that whenever a is greater than b to the power d, then t of n is big theta of n to the power log a with the base b. These results of the master theorems will also hold if we want to have an estimate in terms of your big O notation instead of the big theta notation. So let's see how you apply this master theorem in terms of certain divide and conquer recurrence relation. So if we recall that in case of your binary search algorithm, the time complexity was written as t of n is going to be equal to t of n half plus of 1. Now if we compare with your divide and concurrence relation, which is written in your master theorem, then t of n is written as a times t n divided by b plus c of n to the power d. If you compare this one, then you can say here a will have the value equal to 1, b is going to be equal to 2, c is going to be equal to 1, d is going to be equal to 0. And if you just compare your value of a, b and d, so this is the case when a can be written as b to the power d. So from the second case of your master theorem, whenever a is going to be equal to b to the power d, you can conclude that t of n is big theta of n to the power d times log of n. Since d is 0 there, so you can say t of n is big theta of n to the power 0 times log of n. And n to the power 0 is 1, so you can conclude from there that t of n is big theta of log of n. So by following our master theorem in case of your time complexity of the binary search algorithm, we can easily deduce that t of n is big theta of log of n. Similarly, if you look at the time complexity in case of your merge sort algorithm, then we can have the following recurrence relation where t of n is written as 2 times of t n half plus of n. And if you compare with the divide and concurrence relation which is given in your master theorem, then you can say you will have the value of a equal to 2 here, b equal to 2 here, c equal to 1 here, and d equal to 1 here. And here also you will have the case when a can be written as b to the power d because both sides are 2. So this side is 2, this side is 2 to the power 1. So 2 is going to be equal to 2. And from again the second case of your master theorem, you can conclude that t of n is a big theta of n to the power d log of n. And d here is 1. So it's going to be a big theta of n log n. So in case of our merge sort algorithm, we can apply our master theorem and we can have this result that t of n is big theta of n log n. Similarly, we can have this third example, and let's suppose we have some divide and conquer algorithm where the time complexity is written as t of n is going to be equal to 2 times t of n half plus of 3. And if you compare with your divide and concurrence relation given in your master theorem, then the value of a is 2 here, the value of b is 2 here, the value of c is 3 here, the value of d is 0 here. So this is the case when your a is greater than b to the power d, because b to the power d here is 2 to the power 0, which is 1 here, so 2 is greater than 1. So then from your case 3 of your recurrence relation, the time complexity t of n for this divide and concurrence relation is big theta of n to the power log of 2. Okay. Similarly, you can have this fourth example, and let's suppose if you have a t of n is related with t of n half plus of n square, then if you follow your given divide and concurrence relation in your master theorem, then the value of a is 1 here, the value of b is 2 here, the value of c is 1 here, the value of d is 2 here. So this is the case when your a is less than b to the power d, and this is your case 1 of your master theorem is going to apply here. And from your case 1, the time complexity t of n is big theta of n square here. Similarly, you can have the another case, example 5, where t of n is related with 8 times of t n half plus of n cube, and if you compare, then the value of a is 8 here because you are dividing the original problem into 8 subproblems of size n by 2. So the b is again 2 here, the c is 1 here, and the d is 3 here. So in this case, you can easily write that 8 is going to be equal to 2 to the power 3. So this is the second case of your master theorem is going to be applicable here. And based on your second case, the time complexity of this function is going to be a big theta of n cube log of n. So for this kind of a divide and conquer based recurrence relation, we can apply our master theorem and we can easily get the big theta estimate for the time complexity of those divide and concurrence algorithms. Similar to the master theorem which was given for the divide and conquer recurrence relation, you will also have a Münster theorem, which is basically a master theorem we're going to apply for another kind of a subtract and conquer recurrence relation. So let's suppose t of n be a function which is defined on some positive integer n such that t of n is written as a times of t n minus b plus f of n, and for some constant a and b greater than 0. Now here is a negative sign, so is a subtract, and is a multiple of a, so it's still a kind of a subtract and conquer algorithm. Okay, so instead of divide and conquer, now you have the subtract and conquer algorithm. And if f of n is big theta of n to the power d, then you will have the following three cases you can conclude about this t of n function. You will say t of n is going to be in big theta of n to the power d if a is less than 1. T of n is going to be big theta of n to the power d times a to the power n divided by b if a is greater than 1 here. And the third case is going to be t of n is big theta of n to the power d plus 1 if a is going to be equal to 1 here. So similar to your master theorem for your divide and conquer recurrence relation, you will have a master theorem for your subtract and conquer recurrence relation, which you call as a Münster theorem. So any recurrence relation which can be written in the form of t of n equal to a times of t n minus b plus f of n, where a and b are greater than 0 and some constant, and if f of n is a big theta of n to the power d, then you can easily conclude that t of n is going to be big theta of n to the power d whenever a is less than 1. Is big theta of n to the power d times a to the power n divided by b if a is greater than 1 here, and is going to be big theta of n to the power d plus 1 if a is going to be equal to 1 here. So you will have these three cases in case of your Münster theorem. Now to look at the example where you can apply this Münster theorem, which is basically a kind of a master theorem for your subtract and conquer recurrence relation. So if you recall from your previous lecture of Tower of Hanoi problems, we wrote that the time complexity of the original problem of size n, t of n, is written as 2 times of t of n minus 1 plus of 1. Now if you compare this recurrence relation with your subtract and conquer recurrence relation given in your Münster theorem, then the value of a here is 2, the value of b here is 1, okay, and the function f of n is 1, which can be written as n to the power 0, so the value of t here is 0. Okay, so from our above theorem, here we'll have the case that your a is greater than 1, and whenever a is greater than 1, then you can conclude from the third case of your Münster theorem that t of n is big theta of n to the power d times a to the power n divided by b. And d is 0 here, so it's going to be big theta of n to the power 0, and a in this case is 2 here, so it's 2 to the power n divided by b, and b here is 1. So if you simplify, then you can make a statement that t of n is big theta of 2 to the power n. Okay, and since this is an estimate in terms of big theta, we can also say that t of n is a big O of 2 to the power n. And if you recall, then the time complexity of your Tower of Hanoi problem was big O of 2 to the power n. Okay, so you can have the same result if you follow your Münster theorem, which you can apply for your subtract and conquer based recurrence relation. So remember, don't ever confuse with the master theorem with your Mister theorem. So the master theorem was the original concept which was given for a divide and conquer recurrence relation. The Mister theorem is similar to your master theorem which is given for your subtract and conquer recurrence relation. So you can remember those with the help of your Tower of Ni problem, which is an example of your subtract and conquer problem, while your binary search algorithm and merge sort algorithm is an example of your divide and conquer recurrence relation. So that's all about this lecture. In our next class, we're going to start our new topic, which is about number theory. Thank you.